I'm re-recording this actually because the first recording was completely screwed up in terms of sound. I always try to check the sound, but maybe sometimes I'm missing it. So if you find a problem with any of the recordings, please immediately report to me through the channel. Okay, so when we want to do global carbon cycle and budgets, we have to look at sources and sinks, and at geologic timescales these are degassing sources and sinks of CO2 from various processes, and those include things like this, where you have subduction processes creating high pressure magma chamber, and that's going to create potentially magma puncturing through the middle of the plate. So you have the solid uppermost mantle here with the oceanic crust on top, which is 3 times more dense than the lighter continental crust. So the ocean crust that is constantly forming and spreading at the mid-ocean ridges subducts to create this process, and that leads to these so-called volcanic arcs like Galapagos and Hawaii, and the magma coming through can degas and produce plenty of CO2 to the atmosphere. You also have metamorphism happening at these subduction locations of continental and oceanic crust, which also includes degassing and source of CO2. We have continents colliding into each other. There are various details that obviously I'm skipping because I'm really not so interested in going into the details of geologic processes and their details. But obviously, as you go below the surface, temperature increases very rapidly, leading to all kinds of metamorphosis, which is what we are interested in, because in these situations the magma builds up, and then when it creates ejections, there is a lot of degassing fluxes, which is what are being estimated for the modern times. It's not easy to estimate them for the past periods, of course. At the mid-ocean ridge, you have the ocean crust forming and spreading out, and you can see the temperatures are very high, so you're going to have convection of seawater happening and metamorphism. So that's called greenstone and green schist metamorphism. But we already talked about MORB degassing, or mid-ocean ridge basalt degassing as well. All these kinds of degassing are sources of CO2, and in the next podcast we will look at the sinks. But there is additional metamorphism called contact metamorphism, where the magma chamber enters the so-called existing aureoles, or contact with the existing rock called a country rock, and that creates gases, CO2 release, which then is going to be degassed into the atmospheric system or within the ocean as well. So we are mostly looking for sources and sink of global carbon cycle, which means what's in the system, ocean, atmosphere system, and land, of course. Various estimates exist from papers over the years. These are fluxes in 10 to the 12 mole per year, or teramole per year. So we are looking at sources and sinks here, and this is modern global carbon cycle budget. So these are not estimates of paleo fluxes. So in terms of CO2 sources, we talked about collisional metamorphism, Indian subcontinent colliding with Asian subcontinent, landmass, and creating Himalayas is one good example. There was flood basalts there over time, forming the delta over India. The subduction metamorphism, diffuse metamorphism. So collisional metamorphism estimate is 0.5 to 7 teramoles per year. Subduction metamorphism is happening at 0.3 to much greater than 1 teramole per year. arc volcanism around the globe is producing 1.5 to 3.5 teramoles per year. Mid-ocean ridges, the Atlantic one being the most famous one, is producing 1 to 5 teramole per year. This is all together. Ocean islands, again, they are in the middle of the continental crust, so they could be dead volcanic mountains, or it could be formed by other tectonic processes, and they have a CO2 source of 0.1 to 3 teramole per year. Reverse weathering, alkalinity to silicon ratio of 1 to 2 that we talked about before, is a source of CO2, as we said, so that's 0.5 to 10 teramole per year. Then there are bicarbonate sources, so they are alkalinity sources. From terrestrial weathering, not including groundwater, we get 11.5 to 23 teramoles per year, so much larger than all these numbers here. Oceanic crust weathering is much smaller at 0.2 to 3.75 teramoles per year, but marine sediment weathering adds 5 to 20 teramoles per year. There are also alkalinity consumption processes, so HCO3 minus sink, the carbonate alkalinity. There is biogenic carbonate, 14 to 25 teramoles per year. Oxygenic carbonate from the sediments and oxygenic carbonate in the oceanic crust. Here 0.5 to 1.5 and 1.5 to 2.4. Basically these are typically formed by methanogenesis of various species living either in the sediment or at the ocean floor that are producing methane, which seeps into existing holes and other geologic features, let's say, and there are various processes that happen from methane that is converted to carbonate. They are called oxygenic carbonate because they are produced locally in situ. Okay, these numbers are also represented graphically in this at this site here, looking at modern flux to the ocean atmosphere system in teramoles per year. Carbonation, decarbonation reactions include continental weathering and marine weathering. So here the marine weathering estimate is much larger, going from about 5 teramoles per year to more than 20 teramoles per year, so slightly greater than continental weathering in terms of CO2 sinks. Obviously, you have to always remember weathering is a CO2 sink. Whether it gets re-released in the ocean from calcium carbonate or reverse weathering depends, but weathering by itself is always a carbon sink. In terms of sources, reverse weathering is a source that we saw. Seems to be pretty small, but as we saw before, some papers have argued that it is still a critical part of atmospheric CO2 regulation over geologic timescales. Collisional metamorphism here is a source of almost 7 or 8 teramole per year. Subduction metamorphism may be small, or maybe there is uncertainty in terms of how large it is as a source of CO2, so decarbonation. Arc volcanism here, which we looked at in the range of 1 to 3 or so. Mid-ocean ridge volcanism, larger range. Ocean island volcanism, and organic carbon oxidation, which is looked at here as HCO3 minus sink, so that produces CO2 flux to the ocean atmosphere system. We will come back and look at other processes that provide modern sinks. So degassing is providing the source of CO2 to atmosphere and ocean. We will look at some sinks, but the table and the graphic representation obviously had both of them, but we will add some more details in the next podcast. Okay, I hope the sound is okay in this one, otherwise I'm going to be really annoyed.